our next speaker is Gabriela Wojtowicz from Poland, and she will tell us about Tensor network technique for quantum transport beyond weak coupling. So she's going to take us from quantum simulation to fully numerical simulation, still of quantum systems. Gabriela, please, the floor is yours.
Thank you for the introduction. Yes, my name is Gabriela Wojtowicz, and today, I'll be switching to numerical calculations, but as it turns out, it's already some very non-trivial tasks. So quantum simulators realized in laboratory try to solve the problem of having a classical computation on a classical computer because it's too expensive, but we also try to fill the gaps of the experiment. So obviously realizing something, you always have to have some tech if what is done correctly, and for that the simulations are necessary. So today I'll be giving a broad overview of what I do. They'll be related to tensor networks, but also the approximate techniques which are used for quantum transport. And therefore I included all my different collaborators. They are coming from my university, which is Jagiellonian University in Krakow, but also from National Institute of Standards of Technology in Gettysburg in the US. So to give you an idea what I'll be talking about, let me introduce some physical models which are done in laboratory. So when we're speaking about quantum transport, what we usually think about is some kind of process of transporting particles across a junction. And what I'll be talking about today is quantum transport of electrons. And one of the simplest case one can think about for this kind of phenomena is a quantum transport in nanotransistors. So right now, the nanoelectronics, the electronics we have in our computers is already on a scale of nanometers, but in order to make it even more efficient and more energy effective, one wants to make that logical gates even smaller. And as you make it smaller and smaller, the quantum phenomena becomes more and more apparent, and therefore we have to include it in a simulation, obviously. However, the quantum phenomena appears there and sort of changes our perspective. It also can be used to our advantage. And one of the very nice examples for that is the quantum heat engine, which is plotted here, like photographed here. And this works almost like a heat engine, but now on different principles, and also because of that has additional features. But one can think also of building a quantum system which works as quantum simulator. But for my perspective, the interesting one is the one realized on silicon-based techniques, when you modify the surface, doping the silicon such that you create a structure which can be effectively used to perform quantum simulation, or basically to realize some kind of quantum phenomena on this level and looking on the electrons. So as you can see here, I showed here 4 photos, but they carry very similar features. First of all, we have some distinct region when there is something going on. For example, here is 3x3 lattice, which can be used to simulate some kind of interaction. Here is a nanotube. There's also some kind of number of quantum dots created on a semiconductor. And also there is some number of gates which serve different purposes. It can be used to probe the state of a system. It can be used to apply voltage to create a current coming across the quantum dot, or it can be used as some kind of source of harvesting the energy for the heat engine. And this is why when we speak about quantum transport, we usually imagine this, the model, which consists of some kind of device, which is here named S. It's potentially very complex, can include strong interactions and many-body interactions, such as density-density interaction. And it is coupled to some environments which are which are large but are diluted, it can be interpreted as this context as I plotted here. So now when we have that system coupled the environment and there's some imbalance in the system, imbalance between the reservoirs, then the particles from the left reservoirs will be pushed through the junction to the particles to the right reservoirs. And this creates a current which is controlled by the state of a system S. Now studying that system, that current, we can learn something about the system and also use it to modify the properties of a system S itself. Now, this seems to be fairly easy problem when we think only about S, but as you can see that environments are very important for what we try to describe, because this is a quantum transport. And what turns out is that for electron system, this problem is very hard to simulate on a classical computer. This is mainly due to the fact that the perturbation of entering these infinite reservoirs has a long time of living inside it, which means that although this coupling to S creates some can be weak, it creates some perturbation to reservoirs, which may further in time influence the dynamics of S. And because of that, we have to include the dynamics of the whole system, and we can't treat the environments as simply Markovian. So this is a very difficult problem to describe. So this is also why people often turn to the approximate methods. And among one of the most useful ones is the extended reservoir approach, which allows to study steady state properties for this scattering region. In this approach, we take our environment and we represent it by some finite number of modes. This is fine. We can say that, okay, we can give an exact result for that representation up to some finite time, right? But we cannot describe the steady state properties with a finite environment. And in that cases, what we would like to do is we would like to include some additional effects which account for the infinite nature of the reservoirs. And this is what is done by a dissipator D as described here. Together, that discrete representation and the dissipation should be able to recover the spectral function. And since we know that the steady state properties depends on the spectral function, regardless of this microscopic description of the spectral function, it is enough to say that we'll be converging to the thermodynamic limit solution for infinite reservoirs. Now we can look on that definition and realize that, of course, we made a couple of approximations. So first and foremost, we can ask what's the proper discretization to choose. The other thing is like what is the proper dissipation rate we should choose. And what turns out is that mainly people use the definition of a spectral function, compare it, and give the answer, what's the proper settings we have to choose in order to have the exact dynamics described. However, this is a very convoluted problem, and it turns out that it is also influenced by the state of a scattering region, which we in principle do not know. So instead of looking on the properties of a spectral function, we look on a response of steady state properties with respect to a dissipation rate and discretization. So first, let us look on the dissipation rate. Regardless of any discretization, the current versus relaxation rate follows a very typical curve, which is called the Kramer's turnover, and it has three distinct regions. First of all, there is a small replenishing region when the gamma is too weak, and then the rate of injecting and depleting particles limits the rate of a current we have through our junction. On the other hand, when the dissipation is very strong, then the form of dissipation works in such way that it limits all of the coherences of this explicit representation we chose, and therefore it also limits the current. Finally, there is also this intermediate regime, which we call a physical scenario. In that range, the current doesn't depend on gamma in a first order, and therefore we can say that it is largely free of features of how we chose the discretization. And the current itself is limited by the state of the scattering region, not the construction of the reservoir. This is the range we would like to target in our simulation, and target it in order to say that we simulate the thermodynamic limit correctly. As you can see here already with 128 modes per reservoir, so per this explicit representation, we already have very good result. But it is never ideal just because we made this kind of number approximation. This doesn't forbid us to use that approach, because we know that the exact solution is given as we increase and improve the discretization we have. And as we include more and more number of modes and have better resolution of the spectral function, we converge closer and closer to the thermodynamic limit. When you check out some of our works, you will also learn that it's not as trivial always, and there are all additional effects which occur. However, the good physical understanding of why they occur allows us to develop a procedure which helps to find the domain of confidence for the extended reservoir approach. It might not be the exact result still, but it will be a valuable solution for a quantum transport given that approach. Valuable in general. So now let me turn to numerical methods we actually use. The procedure I just described is already some approximation of the problem, but the master equation we defined has to be solved sometimes, somehow. So in order to solve it, we can write that Hilbert's place explicitly and use some exact diagonalization. However, if we really would like to study very fine discretization of reservoirs, then this model we choose is very large, and this is something which cannot be solved on a classical computer efficiently, just because the size of the matrices will grow exponentially with the system size. So instead, what we do is we turn to tensor networks. And tensor networks is just another way of representing the same problem, and it is very similar to the composition of some very complex data set into product of tensors, where each tensor represents some number of variables, and the network is created by the correlations there is between different variables. So when it comes to a quantum state, then we can imagine this kind of decomposition in a following way. So we have the state vector written like this when it's spanned by some kind of basis vectors. And now each vector comes with a coefficient which can be indexed by the physical indices we have for the basis state. We can look on this coefficient matrix, and instead of writing it in a similar way as for exact diagonalization, we can decompose it in a smaller tensor or the other representation by performing separation of variables. This can be conveniently done with Schmidt value decomposition, and it allows us to separate the big multidimensional tensor into smaller tensors, each holding the variables corresponding to a site 1, 2, and so on. Now we have the physical indexes occurring, also the virtual index, which is responsible for encoding what's the relation between particle 1 or the site 1 and site 2. Besides of the fact that the virtual index is another dimension which also increases the cost of the representation, it also carries some physical information. This is actually a very nice property of tensor networks, that the representation we choose is something which represents something physical. As I said, this is correlation, so in quantum systems it can be interpreted as entanglement. And in fact, the higher the entanglement, the more costly is the representation of the state under tensor networks. So now we can take this method and apply it for a quantum transport when we write the model we just developed in that terms. So as I said, the tensor networks depends on an entanglement. So the cost of tensor networks depends on an entanglement. But it's not only about the entanglement, but it's also how you make that entanglement. So if you find a representation, so if you find a basis which allows you to lower the entanglement calculated on a bipartition between different sides, then that will be more beneficial representation for tensor networks. And what we can do is that we can analyze the correlation structure for the extended reservoir approach and find what's the best tensor network representation, which allows you to mitigate the cost flowing. So briefly speaking, let me just give here an example for that. On the right side, you have the correlation matrix for a steady state current. And on the left side, you have the model. And you can imagine that you can observe here that the correlation mainly happens between the modes of a similar energy, which is natural when thinking of elastic tunneling. And that suggests that we would like to have the correlation, the tensor networks answered to be in energy space, such that we take the least number of cuts across between energies of the same size, just because in elastic scattering, the particle from left of some energy will tunnel to from a mode omega k in left to the mode omega k in right. So this will create some kind of, we'll share some particle Hall pair, adding up to the overall entanglement in our lattice. So let me just quickly show you what will be the best approximation, representation. Here, the energy modes of the reservoirs are ordered adjacent to energy, and also the system S is put inside of the whole lattice, such that the highly contributed current, which are in the bias window, are close to the scattering element. And now within this, we can perform various calculations. In most of our papers, we discuss the convergence of that method and also how to perform it efficiently, and also give some examples for more complicated cases, for example, including many-body interactions. Let me close with this. What I was talking about was mainly related to quantum transport of electrons, and it included the description of extended reservoir approach, which can be used to simulate quantum transport for general problem, including many-body interaction and beyond weak coupling and linear response. I was talking about tensor networks, which enable our exact simulation for a moderate or limited cost. And also together, these two elements allows us to perform to develop general, controllable, and exact method, which enable a large-scale simulation. Before I close, I also would like to advertise our own tensor network code, which you can check out on GitHub. And thank you for your attention.
Thank you very much, Gabriela. Very nice talk. So we can take some questions, if any. Please don't hesitate to post your questions on the Zoom chat. If there is no question, I will have one. Please, Gabriela, is there any entanglement threshold required for your tensor network approach to be accurate, to be efficient?
Is it a threshold?
Yeah.
Well, it depends how much are you willing to pay. So The higher the entanglement, the higher the bond dimension we require. That means that if you set some bond dimension, which is your upper level of a cost you would like to pay, then this will be something which limits the overall entanglement you can encode exactly, right? Otherwise, you encode it approximately and you pay some error, which is called usually a truncation error.
Great. So you said that you are aiming to minimize costs. Can you tell us a little bit more about what kind of costs are you exactly aiming to minimize in your approach?
Yeah, so the minimization of cost was mainly related to the minimization of entanglement we take to encode, and so it is related to the fact that the scattering region is a place when, or maybe like in the quantum transport, the particles coming flow left goes through the scattering region to right, and that means that in a naive approach, when you just take this kind of model as in here and put it into the tensor networks, then the particle from left and the particle, or sorry, the mode on left and right will share an entanglement pair. And the more entanglement pairs you have to encode across your tensor network, the more the tensor network costs. So the more the bond dimension, which is that virtual bond dimension, right? So in order to minimize the cost, you would like to make that entanglement the most local and the least overlapping. And this is basically what we do by imposing this kind of ordering on the tensor network lattice.
Okay, great. So more questions that just popped out on the chat. Any book you recommend to get started with tensor network simulation?
Yeah, I can. I would be able to send it if that person sends
maybe
me.
this